So, when you look in a mirror, do you remain the same person? Like, does it change the reality, or it just the fundamental you, but some kind of rearranged version? So, this is the question which we are going to address in quantum mechanics. Okay. So, imagine that there is a particle in box or an electron which is trapped in potential veil, and if we flip this space around, okay, flipping this space around means you are just replacing the x with minus x. So this is what we are calling flipping. So if we are flipping the space around it, okay, so does the quantum state also change? Does the quantum state associated with it also change? Okay, or the energy of the system changes? And if not, then what exactly changes? So this is the essence of what we call parity in quantum mechanics. Okay, so parity is behavior when you do a spatial reflection. When you do a spatial reflection. A spatial reflection means you take the x and then you replace it by minus x. This is what we are calling a spatial reflection. So we are going to explore these questions step by step. We will see why symmetric potential guarantee parity symmetry, and why wave functions in one dimension must be either odd or even, and how in the higher dimension parity comes to degeneracy. Of course, there is one another concept where you have degeneracy. So where what happens, where more than like one wave function which are linearly independent do have the same eigenvalue. Okay, so when more than one eigenfunction which are linearly independent do have same eigenvalue, so we will know it. Okay, so along the way we will know that symmetry not only organizes our understanding of the solutions, it also saves the hard work which we are going to do, like we actually try to solve this Schrodinger equation. Okay, so in quantum mechanics you should know that what is the most basic part of it. So most basic part of it is that you have this quantum state. Okay, you define that as per the Schrodinger's equation. So you get a differential equation actually, and that differential equation provides a solution which we call wave function. Now this wave function contains all the information, contains all the information required, and which you extract. Okay, so from the wave function you can use a momentum operator p, or position operator, or say Hamiltonian, and you can get the different measurable, okay, which are momentum, position, or its energy. So this is what we do basically in quantum mechanics. This is the essence of quantum mechanics. This is the essence of quantum mechanics. So this work will be saved when you have the symmetric potential. Symmetric potential means you have the potential function Vx which is equal to V of minus x. Okay, so you can see that this is the uh, wave function. This is the x-axis and y-axis, and this is what we are trying to plot the symmetric potential, and we can have this is the potential of linear harmonic oscillator. Okay, this is what we are familiar with, linear harmonic oscillator. You know it already. Okay, so if the potential energy is symmetric about origin, then both psi x and psi of minus x will solve the corresponding Schrodinger equation with the same energy. So what will happen? So you have this Schrodinger wave equation where here you have the form. So you solve this, so you will get the solution that psi of x is also a solution, but psi of minus x also is also a solution. but right now we don't know whether they are linearly dependent or linearly independent. Okay, right now, so we will check for the both cases, linearly dependent or independent is unknown, we don't know it yet. Okay, so it does not mean that the energy levels are automatically degenerate. Okay, it depends on the linear dependence. So degeneracy is more than one linearly independent solution. Okay, so linearly independence means suppose there is one wave function psi 1 and another wave function psi 2, and if you could write that psi 1 is some constant c times psi 2, then one is depending on another. Okay, so you just need to know c, and you will also be able to understand what is the nature of psi 2 from psi 1 or psi 1 from psi 2. So you just need to know c. So this is what we call dependence. And what kind of dependence, to be exact? Linear dependence. So this is the condition for the linear dependence, but there might be some condition where you cannot express psi 1 and psi 2 in term of each other. There is no interrelation. Okay, direct interrelation of any kind, so they are entirely distinct. Okay, so in the quantum state, or even if suppose in the simplest form, you have the vector v1 and you have vector v2, and if you know that vector v1 is some constant c times vector v2, then that does not change the nature of the vector uh, v2. Okay, it is same, just that it is slightly elongated, the nature remains same except that the magnitude changes. So similar happens in this case. Linear dependence changes nothing except that it is some kind of transformation which is just in the magnitude. So overall the nature remains same. Okay, and in quantum state it does not change the description of that quantum system. So that is why if these wave functions are linearly dependent, they does not corresponds to degeneracy, because if the energy eigenvalue is same for two energy eigenfunction, we say that there might be the condition of degeneracy. But when those wave functions are linearly independent. Okay, so that is the crux. So if I say when we can we say that there is a degeneracy. So degeneracy is the concept when you have linearly independent wave function having same eigenvalue and I think you must be aware of the relationship of um, eigenfunction and eigenvalue. So eigenfunction is just a wave function, but if you operate suppose a Hamiltonian on a given eigenfunction function psi 1, and you get energy E, and again that same eigenfunction, then you can say that this is eigenvalue, this is eigenvalue, and this is eigenfunction. Okay, but there might be another case where Hamiltonian of psi 2 is also leading you to same energy eigenvalue. Okay, so in that case we have one doubt that there might be the case of degeneracy, but provided that psi 1 and psi 2 are linearly independent, are linearly independent means psi 1 cannot be written as c times psi 2. You cannot write it, they are not depending on each other. Okay? So only in this case we can say that okay, psi 1 and psi 2 are degenerate. Okay, so that is they are linearly independent, they are corresponding to same eigenvalue, and that is why they are independent. And suppose if we have separate eigenvalue e1 and e2, then this is not the case for degeneracy. Okay, so this is what I wanted to state. So this is the case for the degeneracy, and if this is the condition, if this is the condition, then this is the case of non-degenerate eigenvalues. And let me tell you, even if you have the same energy but the eigenvalues are linearly dependent, then that does not still counts to degeneracy. So this is what you have to be clear. Okay, now let me tell you very clearly that for the system, when you have the potential, where Vx is equal to V of minus x, then what you can do, you can have two wave functions, psi of x and psi of minus x. Okay, and they both corresponds to same energy. They both corresponds to same energy eigenvalue. Okay, so we have to ascertain both the case, the first the degenerate case and second the non-degenerate case. So it will lead to two condition, it will lead to two condition. Condition one is simply that corresponding wave functions are linearly dependent. And linearly dependent means simply it is non-degenerate case, non-degenerate case. And the second one is linearly independent. So it is the case for the degenerate, when obviously you have uh, same eigenvalue for different eigenfunction. That is the crux. Okay, same eigenvalue for different eigenfunction. This should also be true. So if that is the condition, so these are the two conditions. And if the case is linearly dependent, okay, so linearly dependent, we know that you can write psi 1 as c times psi 2. So let's assume that psi of minus x is equal to c times psi of x. This is what we can write, because we are taking one wave function psi of minus x at psi 1 and psi of x at psi 2. Okay, this is the first case. Now we can again try to reflect. Okay, so we can take this minus x to be again minus x. This is the reflection which we want. So it will lead you to um, some constant c again times and psi of minus x. So we have followed one only here. Okay, and now you can see that this psi of minus x is actually psi of x. Like if you reflect something two times, you are going back to the same condition. Okay, so this is psi x and this is c times psi of minus x. And now you can have the representation, okay, where you can write that psi of minus x, this value, okay, to be c times psi of x. So it is going to be c times c of psi x. So now we can write with this that psi of x is equal to c square psi of x, and that means c square is going to be 1, which is equal to c equals to plus or minus 1. So this is the one important result which we have just derived when we know that they are linearly dependent solution of the Schrodinger wave equation. So in that case, what we can write, okay, so if they are just the potential is symmetric, so we can write that psi of x is c times psi of c times psi of x. Okay, psi of minus x is equal to c times psi of x, and c could have two values, one is plus 1, another is minus 1. So psi of minus x is equal to psi of x, or psi of minus x is equal to minus psi of x. So we know this condition as even parity, and it is important one. It is known as even parity, and it is known as odd parity. Okay, so it is just giving you the relationship in between both the wave functions. So it is very easy. Now why it is easy? So suppose you have this curve here, okay, for the linear simple harmonic oscillator, and you want to save your mathematical computation times, you will just find the or solve this Schrodinger wave equation in x greater than 0 region, and then use the corresponding parity relationship, and you can get the answer in the region where x is negative. So this is the beauty of this parity relationship, that if you know the nature of the potential symmetric, you know the corresponding parity relationship, then you can work in only one single space where x is greater than 0. Then you can automatically get the quantum states of the region where x is less than 0. So this was this case when we were just assuming the case for linearly dependent uh, case. Okay, this. So for the linear dependence, we know that psi 1 is equal to c times psi 2. But what if the case is uh, linearly independent case? Linearly independent case. So we don't know. So in this case, we just know that psi 1 is not equal to any constant c times psi 2. That is why we are calling them independent. See the name, that psi 1 and psi 2 are not depending on each other with just some constant. So this is why we are naming it linearly independent. Okay, so in this case, what we can do just one simple thing, that we know that if psi of x and psi of minus x are two solutions of same Schrodinger's wave equation, then any linear combination of them are also the solution. So we can say that, okay, we have two linear combinations, psi of x plus psi of minus x, and psi of x minus psi of minus x. These are two combination, and let us call it psi plus and psi minus. So if this psi x and this psi of minus x is solution, then their linear combinations, which are psi plus and psi minus, are also the solution. Okay, and if you check, then this will be actually of the even parity relationship, and this will be actually the odd parity relationship. Okay, how to check? You know that any function is the even function if that function shows this relationship, and so this is the even function, it results into even parity. And if f of minus x is equal to minus f of x, then this is odd parity or odd function. So this is what you need to know. Okay, so I think we have covered the parity in detail, and the only beauty is that what we just explained here, that you just need to find whatever is happening in the region x greater than 0. You know the exact parity relationship, whether it is even parity or odd parity. Then you apply that using the mathematical formulation, and you will get the answer in the x less than 0 as well. And this has been asked in UPSC CSC as a PYQ too. Okay, so we will get to know that as well. So this whole parity was just to understand that how wave function behaves under the spatial reflection when you are simply exchanging x with minus x. So you are just flipping the uh, space and you are checking what happens to quantum state. That's it.